Hi, I'm Alora, and this is our Physics 212, Project 2, and the problem that we decided on was ropes with mass. I'm going to walk you through the similarities, the differences, limitations, and also our new model overall. Now onto the similarities between ropes that have mass and ropes that are massless. So we can still use F equals ma, which is Newton's second law, to analyze the motion for objects and for the rope itself. And then also the rope and objects are still inextensible. So they're stuck together and they have the same magnitude and acceleration. And then the overall job of the rope is still the same, to pass pulling force tension from one point to another. Essentially, we can still pull a rope. And in both the old and new models, tension is always a pulling force that acts along the direction of the rope. Our force of definition essentially doesn't change. Now on to differences. So we have four different focuses. We have tension, total mass, acceleration, and the main idea. So for when rope is massless, the pull on the rope is the same everywhere along its length. And then when the rope has mass, the pull on the rope is different everywhere because it's the strongest when you pull and it's the weakest at the end of the load. And then for total mass, when the rope is massless, we only count the masses of the objects being pulled. And then when the rope has mass, the heavy rope adds extra mass, so the system speeds up less for the amount of pull. And then for acceleration, when the rope is massless, a lot of pull makes the system speed up a lot. And then when the rope has mass, the heavy rope adds extra mass, so the system speeds up less for the same amount of pull. And then for our overall main idea, when the rope is massless, we only look at the objects. And then when the rope has mass, we have to look at the objects and separate the pieces of the rope, which Ava will talk about later on in our video. Now on to limitations. So this is why our models aren't perfect. Ropes in the real world will always have mass, as we know, and our previous models were a shortcut for easier problems. And then because it was massless, the tension is the same everywhere, which isn't true when the rope is moving and accelerating. And then for our new mass model, we can still assume that the rope can't stretch, but real ropes can a bit, which changes how they pull. Similar to the idea of a carnival rope ladder, like one of those games. Those tend to stretch when someone stands or puts their weight on it. And then we can assume that the rope is perfectly straight, ignoring that it might droop or sag if it's very long or heavy. This becomes important for things like suspension bridges. This is because it needs to sag, because a sag is essential for spreading the massive weight of the bridge deck and the traffic it carries. And then we can assume that the rope is the same way everywhere, but not somewheres. We'll change that over time.
Hi, my name is Ava. I'm going to talk about how our model has adapted to include massive ropes. The way that we are going to include massive ropes in our model is through force analysis. In some situations, it would probably be better to use energy analysis. However, for a lot of the situations that we deal with in physics, I believe that force analysis is going to be more applicable and overall easier to use. So first we're going to run through our current model. What we know about our current model is that our ropes have always been massless and inextensible, so they're not stretchy. What this means is that the tension is uniform everywhere along the rope, even if the system is accelerating. So say you were pulling a sled with a rope, the tension along the entire rope would still be the same, whereas this is not going to be true in our new model. Often we would get drawings that kind of look like this, where we have a mass hanging from a rope, and then our free body diagram would kind of look like something over to the right where we have this mass and we have the force of gravity and the force of tension, and that's it acting on the system. We don't have to include the rope at all. However, with our new model, we still know that ropes are force transporters, so they're kind of acting as the middleman between whatever is pulling the object, like acting the force of tension, say it's a wall, say it's a person, whatever, and the object itself, or maybe it's just the rope hanging there, but yeah, it's transporting a force. Our new scenarios are going to have constant mass density. So we know that the ropes aren't going to be lumpy, have any knots, be heavier at one end or anything. It's going to be uniform throughout the entire length. They're still inextensible, and because of the rope having mass, now the tension is going to vary along the rope. We are also going to, we know that Newton's second law still applies, so the sum of forces on the rope is going to be equal to the mass times the acceleration of the system. What's unknown is what are we going to do now? How are we going to solve these problems with a rope with mass? So what we're going to look at to kind of explain this is force analysis. So say we have a rope that has a length L. So this rope here goes from 0 to L. And what we're going to do to kind of to be able to calculate the tension anywhere along this rope is we're going to take this tiny little piece, which is the piece that's in between the black lines here, and we're going to solve for the tension in that piece. So that way you can solve for the tension along the entire rope or the tension of the rope. The tension force that's acting on the rope, and then you'll be able to add this to your system. So you would probably have to add this to a block. Like if you were saying like, oh, what's the tension force in the system? You'd have to add the tension from the rope that's acting on the rope to the tension that is acting on the block. So yes, our equations we have at the bottom, we have T of x equals T naught, which is the tension of the rope at the leftmost end, in this case, where 0 is, or let's say you had like a hanging rope, it's going to be up here at the top of the Y. It depends on how you define your system, so that T naught is like your initial T, or like at where x is 0, and then we're adding that to mu ax. Mu is the linear or the mass density of the rope, a is the acceleration of the system, and x is how far you are along the rope. And if our system's not accelerating, we're going to be using the equation T of x equals T naught. So it's going to be the same throughout the entire rope if the system is not accelerating. Next, we're kind of going to look at how we calculated this new model, new equation. I used a University of Arizona textbook to help me out a lot with this. Which will be in our sources at the end. So we're still including our Newton's second law of force is equal to the mass of the rope times the acceleration of the system. So looking back at our slide, if you notice, over here we have this T of x on the left side. That's going to be pulling this tiny little piece to the left, so it's negative. And then we have our T of x plus dx, which is pulling it to the right, so that's going to be positive. So for our sum of forces, we have that here. We have our T of x plus dx minus T of x, because it's pulling it to the right, is equal to the mass times the acceleration. We know that the mass of this little piece of the rope is going to be equal to the mass density mu times dx, so times that small distance. That's going to give you the mass of that small piece. We also know that the left hand of the equation is equal to the derivative of T of x dx is equal to our mu dxa after canceling out our d of x on both sides. From here, you can take an integral, and that's when we reach our final equation that T of x is equal to T naught plus mu ax. Kind of an explanation of this equation, a further like looking at the variables. So we're looking at the mass density of the rope. This is important. We know that it's constant. So when you do this equation, or when you use this, like this is going to be a constant, which is why when we took that integral, it doesn't have an x added to itself. So it's not like a mu x plus ax or anything like that. We have x, the distance from the left end of the rope. This is obviously important if you're trying to find the tension at a specific point on the rope. You're going to need a variable that allows you to move and change. So this is our changing variable. And we have a, the acceleration of the rope or the system. So like whatever speed you're pulling your sled at, or if it's just a hanging mass, that's going to be equal to the force of gravity. So another important thing to know, because we are using Newton's second law to define the system. And then T naught, which again is the tension at the leftmost end of the rope or top, or whatever you define your system, the T naught is like the at 0, like what the tension is of the rope. And then to the right, we have again the equation when we don't have an acceleration in the system, where that T of x is just equal to that T naught. I hope this helps. Next, you're going to be looking at some real world applications of this rope with massive rope, and how it applies to everyday situations. Thank you.
So now that we understand how the physics model works, let's try and apply it to a real world example. So let's consider a massive rope with a mass attached to it. So it's going to be this chain that has a box attached to it, and then that chain is attached to a ceiling. The mass of the rope is relevant to the situation because it affects the forces that act on the object, the box, most specifically the tension force. So without the new model, we don't consider the mass, meaning that we don't consider the amount of additional force that is required to hold up both the chain and the box, and this can lead to major problems and accidents. So let's take a look mathematically how that looks. So in the original physics model, we would consider the tension here be equivalent to tension Tx, because it's almost like the only weight that matters is the box, and that's not true. So if we didn't consider the mass of the box, and we like made a ceiling that could only hold up a certain weight, and that's only the weight of the box and not the weight of the chain, the ceiling would break and probably fall on somebody, which we don't want. So it's very important in real world scenarios to consider the mass of the rope. Now let's consider using our new model with the situation. So with this new model, we have to consider the mass of the rope. And with the mass of the rope, we have to consider the additional force that the rope can cause at certain points. So let's look at the ceiling. We look at T naught. We're going to call it T naught. That is the point between the ceiling and the rope. And the tension force there is going to be equivalent to the weight of the rope plus the weight of the box, because at that point in the ceiling, it's basically pulling on both those items. With this new model, we can also consider the mass of the rope at every point using the equation Tx equals T naught minus the mass density of the rope times acceleration times the distance along that rope. This is really helpful because it's not like we're going to use the same length of rope for every single situation. The longer a piece of rope, the heavier it's going to be because it has more mass. So using Tx equals T naught minus the mass density times the distance along the rope, you're basically taking the point at the very top here and subtracting a little bit and a little bit, a little bit down, 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 so that you can only consider like this portion of the rope. So if I were to cut the rope along here, then if I use this equation, I'd be going from here to here and only considering the tension that is right here according to the mass density, acceleration, and distance. Assuming constant density and no inextensibility, this model helps to explain the effect of the mass of the rope when another mass is attached. So this is also applicable to things like cranes, pulleys, cables, those kind of things that require really, really strong material that are pretty heavy. And so without this kind of model, we would run into a lot of problems with things dropping to the ground. But with this model, we can consider additional force and also figure out what is needed and what is not needed when it comes to the mass of the rope.